Okay. Stop. Your standard recording warning. Recursion lecture 12, not 11. So this is the second last lecture. So next week will be the last. This technically is your last lecture where I'm delivering content which you're which I can test you on. So next week I'm just going to give the lecture on complexity, which you're not going to be tested on. And I'll also just add in some fun topics about maybe dynamic programming. I may teach you how to solve the Sudoku puzzle, like write a program to solve Sudoku using a strategy called backtracking. So I'm going to do complexity, which you should know about but won't be tested on, and then some topics to tell you where you're going to be heading after you take this class, right? So for some of you, this may be your last class. Okay, so recursion. So another advertisement for my Comp 3400 class where we're exclusively using recursion to solve all problems, right? In fact, we are obligated to use recursion to solve all problems. This is one of my favorite strategies when writing code because it allows you to solve very difficult problems using very few lines of code in an extremely elegant way. The problem with recursion, it's often hard to sort of wrap your head around because what you're doing is using the function itself when defining the function, which seems sort of strange and magical. So our first explanation of recursion is going to be through memes. So let's look at some memes to describe recursion. Recursion, it recurs. Recursion, it recurs, and so on and so forth. Or you may have observed recursion before in real life, right? When you've been standing in maybe a toilet where they have like two mirrors like across from each other, and it just sort of keeps self-referencing one another. Self-referencing is going to be the name of the game here. Is this a recursion? Is this a recursion? Yes, right? Self-referencing, it's a recursion. Here's a Google troll. Recursion. Did you mean recursion? Right. This is actually what will show up if you type in recursion properly into the Googles. It will troll you a little bit. When I was studying, I remember I had a data structures book, and in that book, I looked up recursion in the index, and I went all the way through the book to the index to find recursion in the index. Right. So I was trolled by a book. in my year 2 studies, and I was really confused as to what was happening until it clicked in. Oh yes, the Drake meme. I think I'm obligated to demonstrate this one. So non-recursive memes and recursive memes, right? I'm going to write a recursive function with a base case, right? So this is going to be something we'll cover. Our recursions will eventually have to stop, and if they don't, they'll self-reference for forever. And then the last one, which is because it's kind of true, to understand recursion, one must first understand recursion. Right? This is the actual genuine strategy that we're going to be employing today. What I usually tell my Comp 3400 students is trust the recursion, right? Trust that the function is working already, and let's design the function. So we're going to flesh this out using a lot of examples today. Okay, so I'm going to show you the principle of mathematical induction. It's going to be a scary mathematical logical statement. So to premise it, just to catch these questions before they occur, you're not going to be tested on induction, nor do you really have to understand induction, but it's the mathematical underpinnings of what recursion is. There's this sort of interplay between inductive proofs and recursive algorithms. So has anyone talked about recursion? Anyone taking a math class where induction, where you've had to maybe write an inductive proof? Yeah, a bunch. That's good. So here it is. This is the statement. So suppose you have some predicate P, and the predicate is asserting some type of truth for every natural number. So for example, the sum of the first n numbers is n plus 1 over 2. So that could be our predicate statement at n. You want to then demonstrate that this statement is true for every natural number. Right? So this becomes sort of tricky. Right? How do you assert the proof of something an infinite number of times? So we have this tool called induction, where effectively what you need to do to prove something is true an infinite number of times is show that it's true at 0, and then show if it's true at the nth step, then it is also true at the n plus 1th step, right? Which means, so if you have it true at p naught, and you have a rule that says you can get from n to n plus 1, then p naught gives you the truth of p1, and p1 gives you the truth of p2, and so on and so forth. Right? So the statement here is, it says p naught, right? You need to show the truth of p naught, and you need to show if pn is true, then it is true at the successor of n, then it is true that for every n, pm is true. And like, people really get tied up with this. Like, there's the self-referencing in recursion is weird, and this is sort of weird in induction, because in order to prove the induction, you need to assume that the predicate is true at n, which seems like the thing that you're trying to prove in the first place. But you're not actually assuming the truth of Pn. You're assuming the truth of Pn as like the antecedent in this logical inference, right? So in order to prove A implies B, you have to first assume A and deduce B. All right, so in prose, this means if the proposition is true for 0, and if the proposition is true for n, then it is also true for the successor of n. Okay, so that may not be very resonant with everyone because it's a mathematical, logical statement. This is my bread and butter. I love writing stuff like this. But I'm going to show you a standard example in induction. There's a bunch of them, but this is my favorite one because it's totally geometric. Okay. So suppose you have a standard chessboard. That's an 8x8 board. And you remove any square from the board. And then I give you these L-shaped dominoes. It's called a trinomino. A domino is a domino because it's two squares connected, but that actually generalizes. So you have this trinomino. It looks like this L. If you remove a square from the board, it's possible to tile the rest of the board. Right? That is, you can place these L-shaped dominoes on the board so that every square is covered and no tile is overlapping. Everyone understand what's happening here? Okay, so the thing then we can prove is we can do this tiling on any board that's 2n by 2n. So like, how would you begin to prove this or even try to demonstrate this? Right, I gave this problem to my Comp 3400 students, and a lot of them try to produce like a generic tiling strategy, which is kind of the right answer, but you can't do this deductively. You have to do it inductively, which is why I give them this problem. So here's how you can use induction to solve this problem. So what did I say were the main components of induction? You have to show that it's true for n equals 0, and you have to show that if it's true at Pn, then it's true at Pn plus 1. So I should state that our proposition n here, Pn, is the statement a 2n by 2n board can be tiled with these trinominos, provided that you remove a square ahead of time. Okay, so P naught then means, can we cover a 2 to the 0 by 2 to the 0 board if we remove a tile? This often tricks people up, right? What's the tiling if I have a 1 by 1 board and I remove that tile? What's the empty tiling? I use 0 tiles, right? We've totally satisfied the predicate condition. I've covered all tiles with trinominos so that no trinomino overlaps and there's no square left uncovered aside from the one I removed. Right, so the secondary part that's confusing about recursion is this base case, right? We're going to talk about a marital argument that I've had. That was one of the worst I've had, and it was regarding these base cases in induction. So the base case indeed is 2n by is 1 by 1. I often see the mistake because this feels uncomfortable. People will say, oh, well, I'll just do the 2 by 2 board because that I feel more comfortable with the 2 by 2 board, right? Because if I remove a square from there, then I can give you the tiling. It's putting it in. But no, you got to go all the way to the bottom. So it is possible to tile with 0 tiles here. Okay, so in induction, there's always something called the induction hypothesis, which is going to be analogous to our recursion. So what we do here is just assume we can tile a 2n by 2n board, which seems like the thing that we're trying to prove, but I'm assuming this as the antecedent, we're assuming this and deducing if this is the case, then it will be the case that the 2n plus 1 by 2n plus 1 board can be tiled. Okay, so assuming that the 2n by 2n board can be tiled, how then can we prove that this board can be tiled? Any ideas? So we want to somehow utilize our assumption. And our assumption being that we can tile the 2n by 2n board if we remove a tile. So how can we produce a 2n by 2n board in this board? What happens if I cut the board into 4 pieces like this? What are the dimensions of those subboards? Yes. So simplify for me. What is 2n plus 1 over 2? You subtract 1 from the numerator. It's 2n by 2n. Yeah, you had it. I just wanted you to simplify one further. Everyone get that? Half of 2n plus 1 is 2 to the n, right? Because 2 to the n plus 1 is the same thing as 2 times 2 to the n, right? You add the exponents, or you subtract them when you're dividing. What do we know about boards that are 2n by 2n? Yes. We can tile them. That's our presumption. So which of these boards can I tile? Yeah. Yeah, this one. So by our assumption, I can tile that. But what happens if I put a tile in the middle here? What have I effectively done to the other 3 subboards? Yeah. Yeah, which means what's true about them? So it's, if I put a tile in the middle, it's like I removed a tile from each of the boards. And by our assumption, all the remaining boards are 2n by 2n boards with the tile removed, and therefore they can be tiled. Therefore, by the principle of mathematical induction, any 2n by 2n board can be tiled with trinominos, provided you remove a square. Yeah. The square is arbitrary, yeah. We'll like write a, so the secondary part of this is to write the code that accomplishes this. Right? Because all you do is you write this code where you're just presuming you have a function which gives you a tiling of a 2n by 2n board. And you can actually, I know it seems magical. We'll write it at the end of class because it's the most difficult one. I don't want to start with the most difficult one. But this is the sort of concept that you have to wrap your head around. You have to assume the thing that you're trying to do is already working, and then utilize that to like build the thing that you're trying to get working. I love this technique, right? Once you get your head wrapped around it, it's so incredibly powerful. Okay, so let's talk about actual recursions, right? Rather than induction. So we can start coding things up today. So here are the ingredients for writing a recursive function. So every recursive function must have at least one base case, right? So we're going to do this infinite like self-referencing. And if that self-referencing doesn't eventually terminate, this is essentially the same thing as like an infinite loop. So what we want is some statement in our function that is somehow, if it's like, if base case, then return constant. There has to be some value that we're returning outright. So a recursive step, and then the second ingredient is a recursive step, right? That is a line in your function which is going to call the function on smaller input, right? And if we do those 2 things properly, right, by the principle of mathematical induction, we will have a function that accomplishes the thing that we need it to. Okay, so the standard or canonical example of recursion is that of the factorial function. So the factorial function is this. So n factorial is just n times n minus 1 times n minus 2 all the way down to 0 factorial. So 0 factorial is 1. We'll talk about why 0 factorial is 1. So what is the factorial? How does it correspond to something meaningful? Like it's the side note down here, right? So the number of ways you can arrange n distinct objects is n factorial, right? So if I have 3 objects, there are 3 options for the first box, 2 options for the second, 1 option for a last. Why then is 0 factorial 1? Yeah. There's one way that you can order an empty collection of objects. It's the empty order. Right, so just keep this in mind, right, when we're writing our base cases, because they really do have to go all the way to the bottom to these empty cases, which may feel uncomfortable. So this is how we could implement the factorial function in Python. And as you see, it has these 2 ingredients that I speak of. There's a case, right, called a base case, where we're returning a constant, where like no more self-referencing is permissible. Right, so just remember that we have these Pythonic 0 checks, right? So when I say not n, this is the Pythonic way of asking if n is equal to 0. Right? It's not my favorite thing in the world, but I'm just trying to program according to PEP 8 standards. Okay, so if not n, if n is 0, then return 1. Otherwise, return n times the factorial of n minus 1. And this just works, right? So if I call a factorial of 0, we enter here, this if statement triggers, and we return 1. If I call a factorial of 3, we're going to go into here. N's going to be 3. And then we get the factorial of 2, which is 2. Right? We assume that that recursive call just works properly. And another thing I tell my Comp 3400 students, don't try and chase the recursion all the way down. Right? You don't have to, you just assume that it's working properly. Right? That's going to give us 6. What is factorial of minus 1 going to give us? Well, what happens in this recursion? Yeah. Pardon? Okay, so we go in here. We get minus 1 times fact of minus 2. What does fact of minus 2 give us? Factorial of minus 3. So what's happening here? Recursion, yeah, but like what specifically then isn't happening? Well, there's no base case, right? So this is called bottoming out. Like we're just infinitely recursing. This is sort of equivalent to like being in an infinite loop, but it's worse. It's worse because every time that I call the function, call any function, that function has to be allocated some space in order to like do its stuff. So not only is this going to loop forever, it's slowly going to allocate all the memory that it's been provisioned. So we have to be careful not to do this. You may get something called the stack overflow error, right? Which means you've allocated too many stacks and you've utilized all your memory. So in Python, you get a sort of recursion error, which is a little bit more informative. And it's saying that you're reaching this maximum recursion depth. So in Python, in order to prevent us from like really utilizing all of our memory, Python puts a hard limit as to how many times a function is actually allowed to like self-reference itself, right? So in the case where we're bottoming out, we'll actually get this error instead of like looping for forever. Okay, so we can investigate how actually this factorial code is operating in memory, right? So if we recall factorial of 4, this is what actually happens. So factorial of 4 calls or like becomes 4 times the factorial of 3, which becomes 4 times 3 times the factorial of 2, which becomes 4 times 3 times 2 times the factorial of 1, which becomes 4 times 3 times 2 times 1 times the factorial of 0. And 0 is factorial of 0 is 1, right? So these are the recursive stacks that I'm talking about, right? Everything is delayed. right? We're like really creating an expression that can be quite big, right? So this is one of the deficiencies of recursion, is that like it's creating the stack rather than just evaluating everything in place. But there are ways of mitigating this, which I'll show you. So this is called the winding phase of the recursion. If you're winding everything up. So during the winding phase, new recursive calls build this stack, and it's a last in, first out stack, right? So the last thing in the stack is the first thing to get evaluated. So you may have to like imagine this is upside down, right? Stacks built from bottom up, and then will be resolved top down. Okay, so after winding, what we have is our unwinding stage. So here's winding, and then unwinding sort of happens like this, right? You start evaluating everything from like the innermost bracket out, and then you eventually get 24, right? So this is like, again, it's best not to try to imagine what's happening here. It's best just to like assume that this is going to return what you need. But for those of you who are wondering like how like this whole thing actually resolves itself, right? This is what happens, right? You build this winding stack of evaluations that are waiting to happen, and then eventually you hit your base case, and then everything starts resolving until you get the answer that you want. Stack overflow. So Python will only allow a finite many recursive calls to be made. This is by design. Exceeding the stack limit does not necessarily mean we're bottoming out, okay? Rather, our algorithms may legitimately require more stacks than what Python provides by default. So you may at some point, okay, so the default number of times you're allowed to self-reference a function is 1,000. You may need to do more than that. So here's how you do more than that. You have to use the system library, and you can say something like sys.setRecursionLimit 1500, right? So that gets you from 1,000 to 1,500. Let's investigate the effects here. So if I do factorial of 998, that's going to give you some preposterously huge number. Okay. If I do factorial of 999, this is going to require 1,000 recursive calls, which means we're going to get a recursion error. Okay. So I can increase the recursion limit by 1, and now this will resolve itself. Right. So it's not necessarily the case if you get a recursion error that you're bottoming out. Your recursion just may require more stacks, so you can always increase it. Nothing is going to save us from this though, right? This is essentially like an infinite loop. So we're going to get a maximum recursion depth exceeded, right? This is called bottoming out, right? Because there is no bottom. Okay, so we're now like converging on the spousal argument that I had. Okay, so we have to now designate base cases. And a very typical mistake by people new to recursion is to not go deep enough in the base case. So in order to deduce the base case, and there is a question like this on your exam, right? Say, here's a recursion without a base case. What is that? Like, what is the base case? Okay. You basically just work backwards, right? You go to the smallest case, which makes sense to you, and just see what the base case has to be in order for the recursion to make sense. Okay. So for example, here's the exponentiation defined recursively, right? So 2 to the power of k is 2 times 2 to the power of k minus 1, right? Effectively, it's 2 times 2 k many times. Okay. But what does it mean to do 2 multiplied by itself 0 many times? Okay, so like, what is 2 to the power of 0? I don't believe that you don't know the answer to this question. What's 2 to the power of 0? 1. Okay, but why? Yeah. Huh? Well, yes, because it has to be, right? If we designated it anything else, like this wouldn't make sense, right? So the smallest case which makes sense here, perhaps, is 2 to the power of 1, right? 2 times itself once clearly is 2. 2 to the power of 1, by my definition, is the same thing as 2 times 2 to the power of 0. And therefore 2 to the power of 0 has to be 1. Has to be. Right? So remember in math, like we're defining these things. Right? So we get to define our base cases like this. Right? So for factorial, it was sort of more sensible because there is a real world analog. For this, maybe not. So let's think of other things. If I wanted to write a recursive function that added the elements of a list together, what should the sum of the empty list be? Well, let's work it out, right? What is the smallest case which makes sense to us when summing an empty list, when summing a list? Well, that's the answer eventually, but suppose we wanted to work this out. Okay, so I'm saying we need to sum a list. What's the smallest list? What's the smallest non-empty list we can work with? A list with one element in it. Okay, so I'm saying so suppose we want to sum the list singleton list 2. That has to be 2 plus the sum of the empty list. So what are we expecting the sum of the singleton list 2 to be? 2. So therefore, what does the sum of the empty list have to be? 0. Okay, one more. Suppose, same question, but instead of taking the sum of the empty list, we want to take the product of the empty list. What is the product of the empty list? 1. Okay, what is the smallest non-empty list? Okay, so we have a list, right? 2 and 3 is in it. The product of that is clearly 6. Let's do a smaller one. We have a list. It's a singleton list of 2. The product of that should be 2. And we have to do 2 times the product of the empty list. Well, we want it to be 2. So 2 times the product of the empty list should be 2. Therefore, the product of the empty list should be 1. Right? So this is weird, right? But you will get this question wrong in your exam if you don't go to the actual base case. Okay. So this is the fight I had with my wife. Right? I was trying to convince a previous class of this, and I went home in despair, saying I just was not able to convince my class of this, and she actually sided with the class. And after 2 hours of trying to convince her of this, I just gave up, and I'm not allowed to mention it anymore. Okay, so I ask you, is an empty basket a basket of fruit? People say no. Okay, but here's my question. How would you validate a basket of fruit is a basket of fruit? Yes, sir. But how do you do, suppose we had to write a program to validate a basket of fruit. A basket was only had fruit in it. Give me an algorithm for checking if there's only fruit in the basket. Okay, so this is how I would do it. Okay, I'd reach into the basket and I take out an item, and I would say, "Is this fruit?" And if the answer is no, then I say this is not a basket of fruit. But if the answer is yes, then I have to put that fruit aside, reach into the basket again, and pull out the next item. Does that seem sensible? Okay, so all the fruit is pulled out. I reach in and I take the last one out, and it's fruit. What then do I have to do now? Right? Well, I have to, so the process was sort of like this. This is a basket of fruit. If I reach into the basket and pull out fruit, one piece of fruit, and what remains is a basket of fruit. That's the inductive way of describing that, which means eventually I pull the last piece of fruit out, and I have to say this is a basket of fruit, provided I take out the last fruit, and what remains is a basket of fruit. Therefore, the empty basket is a basket of fruit. Yes. But it's a basket of anything. That's my point, right? Okay, so we're talking this is semantics, right? This is what everyone tells me every single year. But it boils down to this: the empty collection is a subcollection of any collection, right? For any set, the empty set is a subset of it. It's true, right? So an empty basket is a basket of cars and chairs. An empty basket is an empty basket of baskets, right? But this is the logical hurdle of why students struggle to get to the very very bottom. Yeah. Yeah, essentially, like an empty basket doesn't fail to be a basket of fruit every year. Yeah. Then it's not a basket of fruit, right? Yeah, because the empty set doesn't, like the empty basket doesn't have anything to disvalidate it as a basket of fruit. Like this is sort of like the axiomatic thing that bothers everyone. But forget about the fruit, right? You all side with my wife, that's fine, right? But you can't argue this, right? This is like one of the axioms of like mathematics, period, right? That the empty set is a sub-collection of any collection, right? That the empty set is an element of the power set of anything, right? Yeah. Exactly, right? There's nothing like an empty basket isn't not a basket of fruit, right? Because there's nothing in it to make it not. Yeah, like okay, so an empty basket, there's nothing to disvalidate it is the same thing as like validating it. Again, every year, right? The whole class argues with me over this point, but you can't argue this. Right? It has to do with the fact that false implies anything. Yes, miss. One more go. Yeah. Yes. Yes. But that is a basket of fruit, right? I wouldn't not have, well, like again, we're just playing an English semantic game. Like, do you agree with this statement? Okay, so X is the collection of all baskets of fruit. Ugh. Do everyone understand now how I got into a 2-hour fight with my wife about this? Right? I would like to move on from this point. Like you can all have this like philosophical discussion on the ed stem, but like again, this is an axiom of set theory. If X is the collection of all baskets of fruit, then the empty basket is among it. Like if you don't believe this, math doesn't work. And that is not an exaggeration, right? This is one of the fundamental axioms of, I'm getting worked up now, right? Of set theory. And we're going to move on. Okay. Jesus, I should have put that question on your exam, right? Is an empty basket a basket of fruit? A, yes. B, true. C, A, right? Something like that. Okay, right. I tell you this because I don't want you to not use the appropriate base case, right? The appropriate base case is always going to be the empty collection of whatever you're collecting. Right. So if you have a list, it's going to be the empty list. If you have a string, it's going to be the empty string. An integer will typically be 0. Right. Don't avoid the actual base case because it feels uncomfortable. Right. It feels uncomfortable that the product of the empty collection is 1. It feels uncomfortable that the sum of the empty list is 0. Right. But it is because we need it to be. Okay. So now we've discussed all the theoretical underpinnings of this. We had our basket of fruit argument. So let's now actually like solve problems recursively, because like this is the interesting part now, like actually writing Python code that is realizing these. Oh geez, how much battery do I have left? That should be fine. Okay, so advice. Ask yourself, does anyone have a USB-C charger? Could I have it, please? Okay, let us now solve problems using recursion. Ask yourself how you would solve this problem if you could solve the problem on smaller examples. Oh, yes, sorry. You get a 7 in the course, right? 7 plus, if I could do that. Okay, so I'll just have this here as an emergency if I really lose power. Okay, so let's solve problems using recursion. And then the way that we have to conceptualize this is, how could we solve the problem at hand if we could solve the smaller problem? Okay. When in doubt about the base case, right? Ask yourself what the base case has to be in order for the recursion to work from like the smallest example that you're like comfortable working with. Determine if a string is a palindrome, that is a word that's equal to its reverse, right? This is easy, but like, what's the obvious way of doing this? Like without recursion, how can you check if a word is equal to its reverse? How do you reverse a string? Any signs of life out there, right? There's minimum 2 ways of reversing a string. Yeah. Yeah, you can just step through a -1 or. Oh, that's the recursive example. I just want to sort of like, I just want to be clear that like, we don't need recursion to solve this problem. There's like a simple 1-line solution to this, right? Just using the standard tools of Python, right? So here's like the obvious answer, right? So race car is a palindrome, deified is a palindrome, squid is not a palindrome, okay? Suppose we wanted to avoid reversing the list, right? Here's how we do it with for loops, right? We just sort of walk through the list and check the first and last position, and we like do this until we hit the middle. Okay, so let's go into here, and now let's code this recursively, okay? Desktop, okay. Okay, so I want to have a function is palindrome. Palindrome. It's going to take a string. How much do I got? 9%. Okay, I think we should be fine. I may have to take a 10-minute break to power up soon. Okay, is palindrome. This is going to return a bool. And then, okay, so let's talk about the base case after. But like, what's the recursive case? So how can I check if a string is a palindrome? Well, I need to check that its first position is equal to its last position. And I need to check what? What's the recursive call that I make here? Yes, miss. On what? Yeah, like I go from 1 to -1. Right. So I check the like, what if something's a palindrome, its first character and last character is the same, and then what's left is a palindrome. Does that make sense? So let's look at this. Okay. Race car. What I'm saying is that in order for race car to be a palindrome, this letter has to be the same as this letter, and the middle has to be a palindrome. Is the middle a palindrome? Why? Well, because its first letter and last letter are the same, and what's left is a palindrome. Is what's left a palindrome? Well, that is the same as that, and what's left is the palindrome, because E itself is a palindrome. Okay, so what's the base case then? Single letter, are you sure? No, I don't think so, because x at naught and x at -1 is going to be the same thing with a single character. Yeah, sir, up there. I gave a slide before this designating what the base cases were for collections. What did I say the base case for a string should be? Oh, but the string doesn't have any characters in it. Is it a string? Right. Yeah, it's the empty string, right? If not x's, is the empty string a palindrome? Because it doesn't fail to be a palindrome. Return true. But like this has to be true. So let's work this out, right? Dad is a palindrome because D is the same as D, And then what's left is a palindrome. So let's get rid of that. Is A a palindrome? Well, yeah, because its first character and last character are the same. And what left is a palindrome, right? So the empty character is a palindrome because it doesn't fail to be one. Okay. So let's just check, confirm that this is working. Whoops. Ooh. Is palindrome like dad, right? Daddy, right? Race car. And then this. Okay, so the base cases are uncomfortable, right? But don't avoid them, right? Because they feel uncomfortable. Like this happens all the time in my Comp 3400 class. Well, they'll do the base case above the actual base case because they just can't get behind buying an empty basket of fruit. Okay. There we go. Okay, so here's a exercise for you to do at home, right? To determine if a sentence is a palindrome, ignoring spaces and punctuation. Okay, so that was maybe an obvious example. What is a less obvious example? So suppose I give you a list of lists, and these lists of lists can be like embedded, or you can have lists of lists of lists. I want to perform an operation called flattening. And when we flatten something, that means to remove all interior brackets, right? To get a flat list like this. This problem at the moment, using our traditional tools, wouldn't be that straightforward. Right, we would effectively have to simulate recursion in order for this to work. Okay, so how can we do this problem? Okay, so let's think about this. Okay, so I have flatten, and then I want to take x's, which is a list, but in actuality, it could be like a list of lists of lists, and I want to return a list of integers. Okay. Okay, so let's do the base case later. But what about the inductive case? So like this is a really informative example. I wonder if I should just let you think about it while I. Would you guys like to try this? Yeah? Okay, so I'm gonna give you like we're gonna take a break so you can try this and so I can charge my laptop. But like really try this, right? This is a really informative example if you can get it right. So because like you have to think about everything. Okay, so it's a strict 10-minute break, and then we'll discuss the solution to this. Okay, so you do it too, chat. I'm gonna pause. Just chat, remind me to restart the recording. Or ideas. Great. Okay, who solved flatten? Anyone have a solution for flatten? Have we thought about this? Or we just spent all of our discussion about fruit? Okay, so let's talk about flatten. And this will really show you the power of the recursion. Okay. So I give you, let's just grab the list out of here. Okay. So how can we solve this, right? So we come in, and let's forget about the base case for now. Or are we comfortable enough just doing the base case already? What is the smallest list that I could give? It's the empty list, right? So if not x's, what is the flatten of the empty list? The empty list. Okay. So what we have to do now is consider this. So let's look at the first element. So x's is not empty. So therefore, I can at least look at its first element. That's guaranteed to exist. What do I have to ask about the first element? What are the two options for the first element to be? Pardon me? It's either a list or an integer, okay? So if the type of this is an integer, what should I do? Right, it's exactly this. Okay, so let's think about this list. So we take one out. Right, so we basically, okay, we take this list, we break it into two pieces, right? One, and like the rest of the list. So this is going to be the interesting part. I take one, okay? So I take that, I make it a list, and then what do I have to add this to? Okay, like at the end, we need one. We want to add it to 2, 3, 4, 5, 6, 7, 8, 9. How do I get this? What is this? Isn't this the flattening of this? Yeah. So don't here, I just have to add the flatten of the rest. Does that make sense? Okay, what happens if it's not, if the first element isn't an integer? What does it mean? It's the list. So what do I have to do to it? Flatten it. And then flatten the rest. Right? So let's see if this works. Whoops. Index header. What did I do? Pardon me? Oh, I didn't. Yes. This is, I have to return these things. Thank you. Yeah. And like I can make more arbitrary lists here. More lists. Right. So this was the strategy here. I just assumed flatten was already working. Right. And I used it. Right. It's working in a very particular way, in a way that it's like working on inputs that are smaller than the input at hand. Right. But this is the way that you have to think. Okay, let's do many more. This is the only way to get good at this. There's the answer. Check if a list of numbers is monotonically increasing. Does everyone know what it means to be monotonically increasing? 1, 2, 3 is monotonically increasing. 1, 2, 2, 2 is not. This one's going to be a little bit easier. How can I check if a list of numbers is monotonically increasing? Yeah. The successor of n is n plus. I'm not quite sure what you mean. So like we have a list like 1, 2, 3. So what do you, and let's call this x. So what do you like, what should I do? No fours, no loops. How do I do? Okay, sorry. How can, when I'm asking these questions, what I mean to say is how can we solve these questions recursively? Right. Okay, so how can I check if a list of numbers is monotonically increasing? Yes, sir. Did everyone hear that? The empty list is monotonically increasing because it fails to not be monotonically increasing. Okay, so, and we'll investigate this more. Return true. Okay, otherwise what? Perfect. Yes. Oh, yes. Good point. So that gentleman said, at this point, we've already assumed that the list has 2 elements in it. So actually, this is why I chose this. We need 2 base cases here, right? If the length of x is 1, is a list of exactly 1 element monotonically increasing? Yes. Why? Because it fails to not be monotonically increasing. All right, so we can check this. Check. 1, 2, 3, 4. True. Check 1, 2, 5, 3, 4, false. Okay, next. Sum the digits of a number. Did it just get way brighter in here? Am I losing? I'm probably just having a stroke. Okay, sum of the digits of a number. So 1, 2, 3 is 1 plus 2 plus 3 is equal to 6. How can I sum the digits of a number? This is very similar to like some of the Shifu examples that I've given you. So like, let's think recursively. How now that we have recursion, could we solve this? Okay. I'll just call this foo. Okay, so def foo x is a list of ints. Okay. We have things like foo of 1, 2, 3 has to be 6. Okay, so like how am I teaching you to do recursion? Like, what should we be thinking here? Let's forget about the base case. Like, let's think about the recursive. Well, what should the base case be here? Good. So the base, if not x is 0, right? That's sensible here. Sometimes it's best to leave the base case last because you need your inductive case to like work out what the sensible base case should be. But if you're thinking about the number 1, 2, 3 and we want 6, like we have to think recursively now. Like what subproblem of this helps you solve the problem? Okay, think of it this way. Suppose I told you that foo of 12 is 3, right? How could you solve the problem now? Right? Foo of 12 is the smaller problem. If I gave you foo of 1, 2, 3, and I told you that foo of 12 is 3, how could you solve this problem? Like what's the only thing you'd have to do? Okay, so think about it this way. Like foo of 1, 2, 3 is the same thing as 3 plus foo of 1, 2. Yeah? So if foo of 1, 2 is working already, all I'd have to do is be able to pull out the 3, right? And like make 1, 2, 3 into 12. Does this make sense to anyone? At least one person? Well, there's no index. Oh, sorry. This shouldn't be a list. This was a string, right? Sorry. Yeah, because it should be something like, oh, not a string, an int, right? Okay, so basically I'm going to do this, right? Implement this. I'm going to pull out the 3. So if I have something like 1, 2, 3 and I mod out by 10, where's my mod out by 10? You're going to get 3, right? So let's, I'm going to say this is return x is mod 10. Okay. So this is going to give me the 3. How could I change 123 into 12? Well, what's the corresponding operator to modulus? Quotient, right? 1, 2, 3 divided by 10 is 12. So I can say plus foo of x's divided by 10. Right? So let's see if this works. Foo of 1, 2, 3, 4, 5, 6. Whoops. Hold on. What did I do? Oh, geez. That's a very typical mistake. Yeah. Yeah. Remind me to return if I don't. Let's try that again. Okay. See 2 lines, right? We can do this, right? So I just assumed that the function was like working already in order to solve the problem. Let's do more. I'm going to give you a list of numbers and I'm going to give you a target. And I want you to determine if there's some sublist of the list that sums to some target. Right? So here's the list: 3, 5, 6, minus 3, 1, 2. And I want you to tell me if I can make the target 9 by like using numbers in that list. Right? So I can make 9 because if 3, 5, and 1 is in the list. And I can make minus 1 because minus 3 and 2 is in the list. So the only thing that you're not allowed to do is use a number twice. So how can I solve this problem using recursive principles? Okay, let's try this. Sublist sum. Sub list sum. Okay, so I'm going to give you a list of integers and some target, which is an int. And we want to report true or false, that we can make it or not. Okay. What do you want to do? Inductive step or base case first? Okay, let's do the inductive step first. So how can I reduce this? How can I solve this problem by presuming I have a different, smaller problem solved? So like what would be smaller in this instance? Like what's the thing that's decreasing? Or what's something here which I can recurse on? The list. Okay, so let's take the list. I'm going to call it this y. Let's break it into two pieces, right? X's and X's. Okay, so X is going to be the first thing. And then that's, actually, I'll call it head and tail. Head, tail. Okay, so the head is X is at 0, and the tail is X is at rest. Okay. Okay, so I'm going to call sublist sum on the tail, but for what target? Yes, sir. We're missing a case. Think of it this way. So I'm trying to make this target in this list. What are the two options for head, right? Either the head of the list is included in the sum, or it isn't included in the sum. If it is included in the sum, then I need to know if I can make target minus head in the tail of the list. If it isn't included in the sum, then I need to know if I could make the sublist sum in the rest of the list. Let's think about this again, right? So, and then we need a base case. So what should the base case be? So if the list is empty, what target am I able to make in the empty list? 0, right? So here I think this should be return not target, right? Check if the target is 0 or not. So let's look back here, right? So, okay, I have something like this. Let's just confirm that it's working first. Oh, what is that? Oh, what is happening? Okay, so can I make sublist sum? Here's my list. Can I make 3, 5? That's 8 and 1. Can I make 9? Whoops. Oh, Targer. Right? Can I make I don't know, 10? Probably. Oh yeah, that's 3, 5. Can I make 50? No. Can I make -7? No. Right? So, okay, let's take a look at this one, which was true, right? I'll try to go through this, right? So sublist sum, I'm saying that like either we're going to use the 3 in the sum or we won't, right? So if I pop this out, so this is going to be equal to, can I make the sublist sum? Whoops. Can I make the sublist sum of 5 in this list, or can I make the sublist sum of 8 in here? And then we keep on recursing, right? So this one, right, would be equal to, can I make the sublist sum of 0 in here? And then the answer is true, because I can always make 0 with the empty list. So that's how that resolved. Okay, we'll keep going. Keep going. Suppose you're standing on a grid at the origin, and you can only move along the x-axis and y-axis in positive increments. How many distinct paths are there to an arbitrary position on the grid? Right, so you're standing on a grid. You can only move north by 1 unit and east by 1 unit. I give you some target. How many ways can I get to the target? All right, so let's think about this, right? So I'll just call it foo, or I'll call it target, okay? So I want to get to this. Okay. We'll call it ways to target. Okay, so you're standing at the origin. I want to get to x, y. What's a base case here? What's the like smallest problem that we know for sure we can solve in this case? Yeah. Okay, so if x and y is the origin, how many paths are there? 1, not 0. Okay, so there's one way, there's one path, the empty path, to get there. Okay, so how now can I use, like, presuming the function is working already, how can I utilize it to solve this problem? Well, what are our only options here? I said we can move up by 1 unit, or we can move right by 1 unit. Okay, so like, what happens if we move north by 1 unit first? Then what problem do I have to solve? Yeah. Okay, so move north by 1 unit. Right, and this means ways to target. If we think, instead of walking to the target, consider like we can move the target towards us. Right, so what I'm going to do is move the target towards us. Ways to target x minus 1 y, and then the other way is move east by 1 unit, which is going to be ways to target x, y minus 1. Now, actually, I need a better base case than this. Since we're subtracting, we can get into the negative region. So if x is less than 0 or y is less than 0, there are 0 ways to get there, because I'm not allowed to move in that direction. Okay, so if I just call this A and I call this B, then I'm just going to return their sum. Okay, because if I okay, so let's think about this. How many paths are there from 0, 0 to 1, 1? 2, right? I move right and then up. That's 1. Or I move up and then right. That's 2. How many paths are there to 1, 2? So that's right, up, up. That's 1. Up, up, right. That's 2. Up, right, up is 3. Okay, so let's see if this works. Ways to target. Let's see. How many ways can I get to 1, 1? That should be 2. How many ways can I get to 1, 2? That should be 3. And now, I think now we're off to the races. 20. Okay, because the number of ways I can get to 1, 2 is the number of ways I can get to 0, 2 plus the number of ways I can get to 1, 1. Right, that's how you have to sort of think about it. I'm pulling the target towards myself. You may have to go home and like think about, like, I know this is like really a brain F, right? This recursion, but if you can wrap your head around it, it is an extremely powerful technique. Okay, so last week we talked about this Towers of Hanoi problem. Did anyone manage to solve it? You did. Did you do it recursively?
Yes.
Great. Good job. That makes up for all of the fruit discussions, I guess. Okay. I gave away the plot last week by accident, because these slides I actually used to demonstrate induction in my other class. And the class kind of laughed, but maybe you'll see it now. So thinking inductively, thinking recursively, if I want to move these 5 disks to the third peg, what is the smaller problem that I can presume to solve this problem? I presume that I can move 4 disks. And if I can solve the problem presuming that I can move 4 of the disks, then I've solved the problem. How can I solve this problem of moving 5? Did you need to be reminded of the game? So the game is I need to move these 5 disks from peg 1 to peg 3. And the only rule is that I can move 1 disk at a time, and no larger disk can be placed over a smaller disk. So how can I move 5 disks if I can move 4 of them? Yes, miss. I move 4 of the disks to the middle one. I move the biggest disk to the end, and then I move those 4 disks to there. And this will give us an algorithm, is what I'm trying to impress upon you. That's enough. This is enough. Okay. And I'll show you, like, we're going to code this up. Like, I'm going to show you that all we need is to program that idea, right? That we have assumed that we can solve the smaller problem, and we get it. Okay. So here's 4 disks. And we're going to program it in such a way where the solution is going to be encoded down here. So we're going to have disks 1 through 4, right? So the first position is going to be the disk. We're going to have pegs 0, 1, and 2. And code this tuple is encoding. Let's move disk 1 to peg 1. And then this means let's move disk 2 to peg 2. So I'm going to show you that this is a full solution. And what we expect to find is that there's going to be a substate of this where, in fact, what we have done is moved 3 disks to the middle. You ready? Okay, so that's moving disk 1 to 1. That's moving disk 2 to peg 2. This is moving disk 1 to peg 2. Disk 3 to peg 1. Disk 1 to peg 0. Disk 2 to peg 1. Disk 1 to peg 1. What's this? This is the subproblem of moving 3 disks from the first peg to the from the 0th peg to the first peg, or the first peg to the second peg, right? And then we move this here, and then by recursively we get to move those 3 pegs to there. So we can solve this problem of moving n disks by presuming we can already move n-1 disks. Okay, so let's code this up. So remember, because the encoding of this problem is going to help us solve it. So remember, the solution we're going to give back is a sequence of tuples where the first member of the tuple is the disk we want to move, and the second member of the tuple is the peg. And we're going to name the pegs 0, 1, and 2 because I think that makes things kind of easier. Or maybe we can try 1, 2, and 3. It always gets kind of hectic. Okay, so Hanoi. Okay, so what we're going to do, we have n, and that is going to be an integer. And then we're going to have 2 pegs. So peg 1. How can I do this? I'm going to call this from 2 to peg. Okay. From peg to peg. And this is going to return a list of tuples of, oops, wrong brackets, list of tuple of int. Okay. So this is going to solve Hanoi for n disks from from peg to peg. And you'll see why we have to do it like this. Okay. So this is sort of more generic. I'm not moving things just from peg 1 to peg 3. I'm moving it from the from peg to the to peg. So ultimately, we're going to want to say Hanoi N from peg 1 to peg 3. Okay, so what is the base case here? What is the easiest? Yes. Yeah. If n is 0, how can we move 0 disks from peg 1 to from some peg to some other peg? Well, it's the empty collection of moves. Yeah. Pardon me? Oh, geez, I always keep, because I'm used to programming in a different language. Okay. So now what I want to do is, okay, so we're at the from peg and we need to move to the to peg. So I need to think. So I want to move disk n. So I have to make sure that I encoded this properly. I'm moving n disks. Yeah. So I want to move. Right. I want to move. Okay. So we need to move disks 1 through n minus 1 to what I'm going to call the off peg. Right. So one of the pegs is empty. Right. If I'm moving from peg 1 to peg 3, then I need to like move the intermediate stack to peg 2. Does that make sense? Right. So think of like what we're trying to do. We're moving 5 disks. I want to move 4 of them. So I want to move 5 disks from peg 1 to peg 3, which means I have to move 4 disks to peg 2. But I'm doing this more generically. I say I want to move 5 disks like from an arbitrary peg to another arbitrary peg. So if this from peg is 1, 2, or 3, and this to peg is 1, 2, or 3, how can I figure out what's not among them? I'm going to call this the off peg. So let's think about this. If I want to move from 1 to 3, the off peg is 2. So how can I get 2 from 1 and 3? Yeah, it's subtracting. This is why I named the pegs 0, 1, and 2. It was kind of easier. Would it be okay with you if I said there's pegs 0, 1, and 2 and refer to them as first, second, and third? Okay, because this means I just have to do 3 minus from peg minus to peg. Okay, so let's see if this works. I want to move from peg 0 to peg 2. That means the empty peg is peg 1. So 3 minus 2 minus 0 is 1. Check. Okay. Suppose I want to go from peg 2 to peg 1. That means the off peg is 0. 3 minus 2 minus 1 is 0. That seems to work out. Did I miss one of them? Okay, suppose I want to move from peg 0 to peg 1. The off peg is 2. So that's 3 minus 1 minus 0 is 2. Okay, so I'm moving from this peg to this peg, and the off peg, like the peg that's not at play here, is that one. So what do I return now? Okay, so what I want to do is I first want to move, I want to perform this move. I want to move n minus 1 of the disks to the off peg. From the from peg to the off peg. And then I want to move the current disk n to the to peg. Okay. So if we think about, okay, so think of the 5 disk example. This means, okay, so to move 5 disks from 0 to 2, this, I want to move, I'll do it like this. First, I want to move 4 disks from 0 to 1. So that's going to be this. Okay. Then move disk 5 from 0 to 2. That's this. I'll just combine it at the end. Okay. Then move 4 disks from 1 to 2. Okay. which is this. From the off peg to the 2 peg. Okay, so to move 5 disks from, move 5 disks from 0 to 2, this is what I do. Move 4 disks from 0 to 1, and I get that recursively. Who cares? We just assume this is working. Then I move disk 5 from 0 to 2. That's what this move set is encoded as. Then move 4 disks from 1 to 2. That's what this gives us recursively. And then I just have to combine this. Okay, so I'm just going to do this. We'll take this. We'll add this. And then we'll add this. Okay. And hopefully, if I did it properly, this should work. So let's move 3 disks from 1 to 2. Oh, wasted. Oh, I called the wrong function. Okay, so let's think. Okay, so let's all use our imaginations. So we have 3 disks on peg 0. So I'm saying move disk 1 to peg 2. Then move disk 2 to peg 1. Then move disk 1 to peg 1. Then move disk 3 to peg 2. Then disk 1 to peg 0, 2 to peg 2, and then 1 to peg 2. It's solved. Right? I can do this with 5 if I wanted. That's the solution for 5. So like we got that, we solved this in like 3 lines, right? And one of the lines is just like, I didn't even really need this as a line. So we've solved this problem in 2 lines, right? Using recursion, right? I don't think such a elegant solution would have been available to us just not having solved this problem recursively. So it really is a nice solution, a nice strategy if you can wrap your head around it. Okay, more. Oh, do you want to do this? Maybe I feel like now I'm overloading it. Do you want? We could solve. Okay, maybe I'll leave this to the last, because I want to show you something about dynamic programming, and then maybe if we have some time, then we can go back. Okay, so one of the deficiencies of recursion is that it could be a lot slower than if you were to solve it imperatively, right? And this is because we have to spin up all of these stacks, right? This winding and unwinding is not efficient, okay? So we have this technique where we can actually prevent our recursions from having to wind and unwind in a sense, by letting our functions remember computations that they've already done. So this is a process called memoization. This is really useful when you have problems with like huge amounts of overlap. Okay, so we're going to do this easy one, and then if time permitting, we'll do sort of a harder one. So is everyone familiar with the Fibonacci numbers? So the Fibonacci numbers is a sequence where every number is the sum of the previous 2 numbers, and the first 2 numbers are 1 and 1. So it's 1, 1, 2, 3, 5, 8, and so on. Okay, so it's not hard for us to program this up. So here's the Fibonacci number. Let's get the nth one. This is going to give us that back. So if n is less than 2, then the answer is 1. Otherwise, it's fib of n minus 1 plus fib of n minus 2. Okay, and this is crazy slow. So let's just do some timing here. So there's a package called timeit. I'm just going to do this. Oops, if name equals main. And we just time it like this. It's kind of strange. So I say timeit, and then I have to put a lambda in here, right? Because it's expecting a function. So I'm just going to say fib of 10, and then I'm going to say do it 3 times. You get a more accurate timing if you let it do it more than once. So let's see, and then I want to print this. Okay, so to do fib of 10 3 times, pretty fast. Okay, let's try doing something more significant. 20. Okay, 30. It's already struggling. Okay, let's try 40. Yeah, that may be. Yeah, maybe that was too far. Let's try 35. So I can have a drink of coffee. Okay, I'm gonna let it run. And while we're 6 seconds. Okay, so what I'm gonna do is so remember for 35, it took 6 seconds. And then I'm gonna code up. I'm gonna let this run for fib of 40. We'll just let it run for the time being. But what I'm gonna do is show you how we can like speed this up by like a stupid amount by implementing a cache, by like letting this function remember things that it has already calculated. So what I'm going to do up here is define a cache, and this cache is just going to be a dictionary. And this dictionary is just going to be a dictionary whose keys are input to fib and whose values are like calculated output. So for example, I know that 1 should go to 1 and that 2 should go to 1. So I can remove this base case. And what we're going to do now instead is I'm going to say if n is in this cache already, don't bother like computing this. Just return the cache at n. Okay. Otherwise, go ahead and calculate this. And once you calculate it, put it into the cache, and then just return the cache. Okay. So I think this is like hopeless that this 40 is going to finish. So I'm just going to stop it. But let's just look at my activity monitor to prove that like this is actually like utilizing all of my memory. If this ever shows up. Oh gee, Zoom is where's Python? This should be, is this not running? Oh, it finished. Oh geez, 76 seconds. Okay. Oh, sorry. Yeah, for 40, it took 76 seconds. Okay. So I gave it a cache. I just want to make sure that it's working before I do anything else. So fib of 3 should be 5. What? Oh, test. What? Two. Is that correct? Oh yeah, 2. 4 should be 5. Is this not working? What should fib of 4 be? 1, 1, 3. Is this working? Yeah. Oh, okay. Okay. Okay, so I have implemented this fib. It has a cache. Any guesses for, okay, so for 40, it took 76 seconds when I didn't implement this cache. Are there any guesses how, like, what kind of like efficiency gain we're expecting here? 10 seconds, 20 seconds, like half the amount of time, 30 seconds. Any guesses? All right, well, let's just run it and find out. 0.00002 seconds. I would say that's a pretty significant efficiency increase. Okay, so this is extremely powerful now, right? We can basically circumvent some of the problems of recursion by like using this caching. Okay, so let's see if we can solve one more problem in the last 5 minutes where we're going to utilize this dynamic caching. Okay, so here's a problem. Here's a string, ABC. The string has 8 substrings. The empty string, A, B, and C, A, B, A, C, B, C, and ABC. If I give you 2 strings, they both have substrings, right? And they're going to have some common substrings. And like one of them or some of them have to be the longest common substring. So I wanted this, I actually put, this was a question on my exam for my Comp 3400 students last term. So I want to write a function that given two strings returns the longest common subsequence of those two strings. Like here's a string, here's another string, and common to both of them is the substring CBBCE. So let's try to get this. Longest common substring of X's, which is a string, Y's, which is a string. This is a string. So I'm just going to try to do this fast. So if X's is empty, then the longest common substring is empty, right? And it's the case that if Y's is empty, the longest common substring is empty. So there is only two options here. So either the first string of X's is equal to the first string of Y's, and then the longest common substring is this, plus the longest common substring of what remains. Longest comes this. Oh, right. Okay, or right, the first character is not included. So then it's the longest common substring of this, or the longest common substring of this. And in fact, it's the whatever one is longer of the two. So I can just do something like this, key equals length. Okay, so let's see if this works. Okay, so let me take this. 4 minutes. Whoops, what did I do? Pardon me? Final return is, I can't hear. Oh, thank you. Okay. So this also has the problem of being quite slow. Let me just pull this up. My solution from yesterday. Longest common subsequence. Okay, so here I have a random string generator. That was fairly easy. And here's the longest common subsequence problem defined as we just did it. And then here's the longest common subsequence, but like I implemented a cache. Now, what I did here is I just ran the longest common subsequence problem, and I'll make it length 10, right? For random strings of length 10. Okay, maybe I can do a little bit longer than that. It should take a little bit of like seconds. So while this is running, I want you to solve that the tiling problem at home, right? The solution, I'll post the solution in the Blackboard, but like try not to look at it before you've given it like an actual try. To make the problem simpler, I made the problem simpler by saying you're allowed to remove whatever square that you want, right? So to make it simple, remove 0, 0. Okay, so I'm trying to solve the longest common subsequence 3 times for strings of length 13. It like still hasn't finished. We're at seconds. Okay, so if I now turn this off and I change this to the dynamic one, the one that has caching, it will finish instantly. Right, so this was a more practical example of like demonstrating that recursion plus caching, this dynamic programming, is an extremely important technique. Okay, so next week, again, I'm just going to show you optionally complexity and some more fun dynamic programming examples, and we're going to solve Sudoku. I'm going to show you the backtracking strategy. But otherwise, if this is your last lecture with me, like, thank you very much for showing up. I'll be around to help you prepare for your exams. And then why don't you all go out and enjoy fruit? Go out and buy a fruit until that basket is empty. And I'll see you next week, right? Bye, chat. Thank you guys as well.